Anyone who regularly flies on commercial aircraft has likely noticed the same curious sensation shortly after takeoff. The engines roar at full intensity during the takeoff roll, the aircraft rotates, and within moments of becoming airborne, the sound suddenly softens as the thrust appears to decrease. For nervous passengers, that brief reduction in power can feel unsettling, especially because it happens at a stage of flight when the aircraft is still climbing away from the runway and remains relatively close to the ground. So in this video, we take a look at why pilots deliberately pull back thrust shortly after lifting off the runway, how modern aircraft rarely need maximum power in the first place, and why this procedure actually improves efficiency, reduces engine wear, and helps keep flights safe. And be sure to check out Simpleflying's flight tracker. From live alerts and data on commercial, military, and government flights, it goes way beyond your standard tracker. It was built specifically for avgeeks, free and live, right at your fingertips. One of the biggest misconceptions surrounding airline operations is the idea that aircraft always depart using every bit of power their engines can produce. While maximum thrust settings are certainly available when conditions require them, the reality is that most commercial flights do not need full takeoff power in normal operations. Rather than using extra performance unnecessarily, pilots often deliberately reduce available thrust before the takeoff roll even begins. This process is known as a reduced thrust takeoff, and airlines generally favor it because operating engines at lower temperatures and stress levels significantly reduces wear over time. Since jet engines are among the most expensive components on an aircraft, extending their service life carries enormous financial benefits for carriers operating large fleets. There are two primary ways pilots reduce engine thrust during takeoff. The first method is known as a derated takeoff, while the second uses what pilots call an assumed temperature or flex temperature calculation. A derated takeoff involves selecting a lower certified engine thrust setting before departure. The aircraft still accelerates safely and meets all regulatory climb requirements, but the engines operate under reduced thermal stress. The second method is more commonly used on many modern aircraft, with pilots entering an assumed outside temperature into the aircraft's flight management system that is significantly higher than the actual ambient temperature. Because jet engines naturally generate less thrust in hotter conditions, the system calculates a lower thrust target corresponding to that temperature. The process is entirely controlled and carefully calculated, ensuring the aircraft still meets all performance requirements. This technique works because takeoff performance calculations account for runway length, aircraft weight, weather conditions, obstacles, and climb capacity, and if enough performance margin exists, there is no operational reason to expose the engines to unnecessary stress. Importantly, full power always remains instantly available. If pilots encounter wind shear, unexpected performance issues, or any abnormal condition during departure, immediately pushing the thrust levers fully forward restores maximum takeoff thrust. The primary reason airlines use reduced thrust departures is surprisingly simple. Engines last longer when they're not constantly operated at maximum output. Jet engines function in extraordinarily harsh environments, with internal temperatures reaching extreme levels during high-power operations. The hottest and most stressful moments in an engine's operating cycle typically occur during takeoff, particularly during long-haul departures where aircraft are near maximum weight. Even relatively small reductions in thrust can dramatically reduce thermal strain, and industry data have shown that reducing takeoff thrust by only a small percentage can significantly improve engine longevity because the final increments of exhaust gas temperature create disproportionate wear on turbine components. That matters enormously for airlines because engine maintenance is staggeringly expensive, as modern engines from the likes of General Electric and Rolls-Royce can cost tens of millions of dollars and require regular overhauls involving specialized inspections and replacement parts. The operational philosophy, therefore, becomes straightforward. If an aircraft only requires a fraction of available thrust to depart safely, there is little reason to use maximum power every time. Airlines instead preserve the engines whenever runway conditions and aircraft performance allow it. While reduced thrust settings before takeoff are important, the phenomenon passengers most commonly notice actually occurs after the aircraft has already become airborne. Once the aircraft reaches a predetermined altitude, pilots intentionally reduce engine power as part of a standardized procedure known as a noise abatement departure procedure, or NADP. These procedures exist because communities surrounding airports have long been affected by aircraft noise. Large jet engines operating at takeoff thrust generate enormous sound levels, particularly when aircraft remain low over residential areas immediately after departure. To reduce that impact, international aviation authorities developed standardized climb profiles that balance aircraft performance, safety, and environmental considerations. Under these procedures, crews reduce thrust at a specified altitude after takeoff, usually somewhere between 800 and 3,000 feet above the airport. The change is very noticeable inside the cabin. Engine noise decreases, acceleration often slows briefly, and passengers sometimes perceive the aircraft as leveling off, even though it continues to climb safely away from the runway. International Civil Aviation Organization standards define two primary noise abatement departure profiles used by airlines around the world. These are commonly referred to as NADP1 and NADP2, and each serves a slightly different purpose depending on airport surroundings and local noise concerns. NADP1 is designed primarily to reduce noise exposure for communities located very close to the airport, and under this profile, aircraft maintain their initial climb configuration for longer after takeoff. Following the thrust reduction at a designated altitude, the aircraft continues climbing at a relatively modest speed until reaching approximately 3,000 feet, before accelerating and retracting additional flap settings. This keeps the aircraft higher over nearby neighborhoods because the slower climb profile prioritizes altitude gain over acceleration. Airports with dense residential areas immediately beyond the runway often prefer this procedure. NADP2 works differently. Under this profile, thrust reduction, acceleration, and flap retraction all begin much earlier, typically around 800 feet above the runway. The aircraft accelerates sooner and transitions more quickly into a clean climb configuration. This procedure benefits communities located farther from the airport because the aircraft reaches higher speeds and cleaner aerodynamic configurations earlier in the departure. Different airports select procedures based on local geography, terrain, population distribution, and environmental restrictions. Regardless of which profile is used, regulations prohibit thrust reductions below certain minimum altitudes. Safety always takes precedence over noise considerations, and crews must maintain sufficient aircraft performance throughout the departure. Airlines also suspend noise abatement procedures entirely during emergencies or abnormal situations. If an engine failure occurs, if wind shear is suspected, or if weather conditions deteriorate unexpectedly, pilots immediately prioritize aircraft performance and handling rather than noise reduction targets. Although reduced thrust procedures are routine throughout commercial aviation, they rely heavily on accurate calculations and rigorous crew coordination. Flight crews calculate performance using detailed software and operational data that account for runway length, temperature, wind, airport elevation, aircraft weight, and obstacle clearance requirements. The resulting calculations establish the minimum thrust required to safely continue the takeoff, even if an engine fails during the departure. One of the principal risks associated with reduced thrust operations involves incorrect data entry, and entering an inaccurate assumed temperature or selecting the wrong thrust setting could, in theory, leave the aircraft with insufficient performance margins. To guard against that possibility, airlines require extensive cross-checking procedures. Both pilots independently verify calculations, confirm runway data, and review flight management system entries before departure clearance is accepted. Modern aircraft such as the Airbus A220 and upcoming Boeing 777X also provide automated monitoring systems that compare expected and actual aircraft performance during the takeoff roll. If acceleration appears abnormal, crews can reject the takeoff before reaching decision speed. The broader reality is that reduced thrust operations have become deeply embedded in global airline procedures, precisely because they are safe when properly executed. What do you think is the most impressive example of how modern aviation uses careful planning and engineering to improve both safety and efficiency at the same time? Let us know by leaving a comment, and don't forget to subscribe for more aviation content. See you next time. In addition to our daily YouTube videos, Simpleflying publishes over 150 articles and a podcast every week. Visit simpleflying.com.